SwayamPrabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. Okay. In the last class we were looking at the mode shapes and natural frequencies of a simply supported cylindrical shell. Okay. We were discussing the nature of the natural frequencies, or rather that we will get 3 sets of natural frequencies and how to find which dimension the dominant motion occurs in. Okay. Now the alpha 3 set of natural frequencies are the lowest, that is what I said. Okay. Now if we, so in the textbook there is an example that can be done. Okay. Example, for a certain dimension cylindrical shell you can compute, the closed form formulas are there. Okay. Now with modes, okay, with modes it turns out that as you go higher, in modes, the strain energy goes up. Because if you have seen the simply supported plate, the first mode is like this, the second mode has more bending, the third mode has even more bending, and so forth. So the strain energy goes up with higher modes. Okay. And now as the oscillations, free oscillations occur, the entire strain energy gets converted to the kinetic energy as the shell vibrates in that mode. Okay. The full strain energy is converted to full kinetic energy at some instant under free vibration. Now the kinetic energy is proportional to the natural frequency squared. Okay. If you even realize you have 1/2 mv square and v is omega times displacement, then this ends up as square of the frequency. Okay, square of the frequency. So what happens is, with the strain energy, the natural frequency goes up. The ones with high strain energy, the modes with high strain energy have high natural frequencies. Or higher order modes have high natural frequencies. Okay. Now because we have now a shell that is curved, okay, the movement, if I stretch this, if I stretch the circumference, I get movement in the alpha 3 direction or u3 direction. Okay, the circumference has been stretched, okay, and that has caused a u3 movement. So all 3 displacements are similarly coupled. So now if we plot these circumferential strain energy, circumferential stretching or membrane strain energy, as a function of n. Okay. So what do I mean? First of all, if we look at the circumference, or if we look at the circumferential direction, okay. So let us say we have chosen one particular type of mode, cos n theta. Okay. For n equal to 0, what happens is the shell will have a breathing behavior. Okay. If that is a nominal diameter, the shell acquires a higher diameter at some part of the vibration and a smaller at some other part, but uniformly. This is unequal to 0. Okay. When you have n equal to 1, what happens is this, as we have seen for the ring, it will oscillate back and forth. Okay, it will oscillate back and forth. This is n equal to 1. Okay. If we look at n equal to 2, you look at n equal to 2, then that is called the ovaling mode. It will go to this shape in one instant and it will go to this shape in the another instant. And if you look at n equal to 2, if you look at n equal to 3, if this is the nominal shape, then it can look like this. This is n equal to 3, and so on. So now for each of these shapes, if we approximately find out how much there is stretching happening, okay, and how much bending is happening in terms of energy, okay, how does it look like? So this is my circumferential number, n equal to 0 here, n equal to 1 here, n equal to 2 here, n equal to 3 here, n equal to 4, n equal to 5. Okay. So now if we try to plot these membrane strain energy, you can see that N0 stretches the maximum. There is a maximum stretching of the membrane. Okay. As the diameter uniformly goes up, the shell stretches. Okay. And if you move towards the right, you can see that this stretching is less now. Stretching goes down. Okay. Whereas there is hardly any bending going here, bending of the shell is hardly there here, whereas if you move towards the right, bending will appear to go up, bending goes up, bending energy goes up. So if we plot, first of all, the membrane strain energy, N0 will be high, N1 may be lower, N2 will be further low, N3 is low, 4 low, 5 etc. Will uniformly go down. Whereas if you look at the bending, so this is membrane, if you look at the bending you will find maybe low here, it goes up here, so it goes up here, it goes up here, it goes up here and so forth. So if you plot a curve which is membrane plus bending, okay, then how will it look? You just add this up, you will see that there will actually be a dip and then it will start going up. Okay, energies, if you just add the energies, you will see that it starts off high, takes a dip, has a minimum somewhere and starts to go up. So the alpha 3 or U3 set of natural frequencies have this phenomenon, have this shape for their natural frequency curves. Because there is significant coupling between membrane energy and bending energy. Okay. So if you take the example, you will see this behavior. Okay. So now what I will just show you, I will show you the M1, which is 1 in the axial direction and 0 in the circumferential direction. Let us see if it runs. Okay, so let me so that is the breeding mode of the cylindrical shell. So there is M is 1, so 1/2 cycle along the length, that is the length, and this is the circumference, so it is breathing uniformly. Okay. One thing of course is that it is simply supported, so I did not support it at the edges, so the movement or displacement at the edge is not correct, okay, but otherwise you get a feel for what is going on. Okay. So let me now stop this. This is the M1 N0 mode. Okay, let me stop this, then let me make it M2 N0 mode. Okay, so you can see that there are 2 half cycles along the length. Okay, there are 2 half cycles along the length if you observe. Next, if I do, let us say N1 over here, M2 N1. You can see that it oscillates in one particular direction and along the length M is 2. Now let us look at M2 N3. Okay, so these are exaggerated, you do not get so much deformation. just to show. So circumferentially you get N3 behavior, axially you get M equal to 2 behavior, 2 half cycles. And so I am dominantly plotting the U3 displacement, okay, or rather I am focusing on the modes where alpha 3 displacement is maximum. So let me now show some very high order, let me say 6 or something, and let me change this to 3. So let us see. Okay. So that is again exaggerated, but so that is how cylindrical shell modes look like. Okay. Now that means what? What that means is that I will have a cosine theta this set of modes, I will have this set of modes, that means cosine n theta, sin n theta, cos n theta. So that is call it set 1. Then I have this second set of modes, sin theta, cos n theta, sin theta set of modes. Okay. They will have the same natural frequencies. In addition, I will have an index I going from 1 to 3, which indicates the natural frequencies of the dominantly axial modes, dominantly torsional modes, dominantly transverse modes. Okay. So the response of all these modes has to be added when you do the force response of a cylindrical shell. Okay. That will come much later. Okay. Now what I want to do is that with this I kind of complete the portion of mode shapes and natural frequencies. Okay. So what did we look at? If we just summarize, we looked at beam modes, okay, cantilever, simply supported and so forth, and we looked at rectangular plates, okay, simply supported, clamped, etc. Then we looked at a circular plate, okay. Then we looked at a ring, okay, ring, okay. Further we looked at a cylindrical shell. Cylindrical shell. Okay. These are simple to show and derive. Now what is important now about mode shapes? Okay, what properties do mode shapes hold? Okay, they satisfy, mode shapes satisfy all the boundary conditions. Mode shapes satisfy all the boundary conditions. Okay, natural, essential, okay, or force, moment and geometric, they satisfy all the boundary conditions. Okay. So they satisfy the partial differential equation, they satisfy the PDE, and they satisfy the all the boundary conditions. So they are very special, they are very special, they are very special or unique, special. Okay, and you would like to know the mode shapes exactly of any system. Okay, so just hypothetically, if you have a very strange system, okay, clamped somewhere, supported somewhere, simply supported somewhere, free somewhere, etc., etc. Okay, and if you manage to find the mode shapes, okay, then you have the problem in hand. Okay, now what else can be said about the mode shapes? Okay, so first of all, when we talk of mode shapes, the system is free. Okay, the system is freely vibrating. The system is freely vibrating, and therefore the external loads or the energy from the external loads is 0. Okay, and since all the boundary conditions are satisfied, the energy from the boundary is also 0. Okay, and so we can work with the Hamilton's law in this form: T1 to T2, the strain energy minus the kinetic energy dt equal to 0. Okay, now I think given you the definition before, that a mode shape often it's a question, what is a mode shape? A mode shape is a shape in which or into which or let me keep it as in which a structure can be given an initial displacement. without violating boundary conditions. That means what? If I have, let us say, a cantilever beam, I have a cantilever beam, then I can give this displacement. I can put a finger here, deform it, okay, this way, and let it go. Okay. If I have a simply supported beam, say I have a simply supported beam, and then this is my actually first mode, so I can deform it in that way at time t equal to 0 and let it go. Okay. So, a mode shape is a shape in which a structure can be given an initial displacement without violating the boundary. So, I am not breaking the bond here and the beam shape is like this or anything like that. Okay. It is in accordance with the boundary conditions, with the constraints. Okay. An initial displacement without violating, and if we let it go subsequently, the structure vibrates in that shape. Freely, of course, and hypothetically forever if no damping. Okay. And every point vibrates at the same frequency, same single frequency. Okay. So, if I deform this beam into this shape and I let it go, then it will start oscillating back and forth. And if I take a measurement of here, a measurement here, or measurement here, in time every point oscillates at the same single frequency. Okay. So, that is a mode shape. Okay. Now, the additional property of these mode shapes is that mode shapes are orthogonal. Mode shapes are orthogonal. Okay. So, this is very valuable. So, now we are going to prove the orthogonality property. Let us see. So, we will use the Hamilton's law to prove it. So, what we now have is that the variation over the time integral of the strain energy minus kinetic energy dt is equal to 0. Okay. And the strain energy T1 to T2 delta of u dt is equal to now integral T1 to T2 integral alpha 1 integral alpha 2 integral alpha 3 sigma 1 1 delta epsilon 1 1 plus sigma 2 2 delta epsilon 2 2 plus sigma 1 2 delta epsilon 1 2 plus sigma 1 3 delta epsilon 1 3 plus sigma 2 3 delta epsilon 2 3. A1 A2 d alpha 1 d alpha 2 d alpha 3 dt. Okay. And the kinetic energy term T1 to T2 is delta k dt is equal to minus rho h integral T1 to T2 integral alpha 1 integral alpha 2 u1 double dot delta u1 plus u2 double dot delta u2 plus u3 double dot delta u3. A1 A2 d alpha 1 d alpha 2 dt. Okay. Now what we are going to do is that ui I running from 1 to 3 representing u1 u2 u3 motions displacements over alpha 1 alpha 2 and t. I am going to say is that is equal to sum u big I k alpha 1 alpha 2 e to the power j omega kt. This is the kth natural frequency, and so this is the kth mode shape. Okay, and I refers to the direction. That means what? u1 will be equal to u1 k in the kth mode, alpha 1 alpha 2, it will be vibrating at omega kt, a single point alpha 1 alpha 2. Okay, a single point on any shell u1 alpha 1 alpha 2 and t will have this movement. The same point u at alpha 1 alpha 2 and t will have a u2 movement of capital U2 k alpha 1 alpha 2 and the same frequency, and the same point will have a displacement in the third direction which is equal to u3 k alpha 1 alpha 2 e to the power of j omega kt. So this entire shape in the three directions is called a mode shape. Okay, it's not that this is one mode shape, that is another mode shape. This, no, a single point, okay, is undergoing this movement, and this entire shape is called a mode shape. Okay, we are running out of time, so I'll stop here for today. We'll continue in the next class. Thank you.